Hello, my name is Christos Profentzas. I'm a PhD student at Chalmers University in Sweden, and today I will talk about our paper, Performance of Deep Neural Networks on Low-Power IoT Devices. Recently, deep neural networks has been on the spot. They have achieved high accuracy for machine learning tasks like image classification. However, deep neural networks are quite computational intensive and they require a lot of memory space. This makes deep neural networks quite questionable to run on a small, cheap, low-power IoT device. The main challenge for running deep neural networks on IoT device is the resource constraints. These devices have limited CPU power with some kilobytes of RAM, and they depend on cheap batteries to operate. However, there is several frameworks that support actually IoT devices with different trade-offs, and they use different methods to compress the model and they targeting different accuracies. In our paper, we like to see what we investigate what networks actually fit on our device and what is the trade-offs. Because it's not so easy to choose a configuration in advance. There is a trade-off between network size, inference time, and each framework give you different automation to generate your code. We investigate in our paper three frameworks, namely TensorFlow, CMSIS, and uTensor. With our paper, we propose a benchmark to evaluate frameworks for IoT deep learning. We focus on inference only on the device. We assume that training is happening in more powerful device, and you try to compress a model and put it in IoT device only for inference purposes. We look into different framework specifications and the difference between the tool chain. All of the frameworks use a high-level language to define and train a network. However, they differ in the quantization methods and the code generation methods, which also lead to some different hardware requirements. For example, CMSIS is part of the ARM Cortex-M architecture, so it focuses on this kind of devices, while TensorFlow is a bigger framework that tries to support also mobile and edge devices. With our benchmark, we have three major evaluation goals. We namely investigate memory, energy, and inference time. Now, I would like to give you an overview of how we set up our experiments. We choose a Cortex-M device with 256 kilobytes of RAM. We train our deep neural networks using we have two types of experiments. One, we have deep neural networks trained on MNIST, which is grayscale handwritten digits, and we train neural networks on CFAR10, which is colored images. And this gives you difference in accuracy, as you can see in the table. And in order to see the consumption and the resource consumption in the device, we scale the convolution kernels that have the most of the parameters of the network, and we scale from 16 to 128 convolution kernels, and each of this is a different deep neural network with different with the same architecture, but we just scale the convolution kernel. Moving to the memory consumption, we find out that a small model with 16 convolution kernels can easily fit in the RAM, consuming only 22 kilobytes. But as you scale your convolution kernel, the memory consumption is quite significant. For example, training a model for CFAR 10 dataset and 128 convolution kernels, we find out that it doesn't fit in the RAM using the CMSIS framework, and barely fits with the other two. However, we have these networks only for demonstration purposes, because even though the other two frameworks fits into the memory, they don't let any, they leave really small memory for the actual application. So in practice, you will use less than 120 kernels for your network. Moving on to the energy consumption, we find out that CMSIS is most efficient over the other networks. This is happening because CMSIS utilizes the digital signal coprocessor of the device, so most of the matrix multiplications happen on a DSP, and this is, as you can see in the graph, there is a spike into the energy consumption, but because DSP is quite efficient to do the matrix multiplications, it takes less time. We find out that the other two networks are not so efficient, but for a small network with 16 convolution networks trained on CFAR 10, the energy consumption is quite satisfactory. However, there is a big difference between the three frameworks, especially energy consumption. The U-tensor takes most of the time to execute the network, which highly influences the energy consumption. So this is why, even though you can see in the graph that TensorFlow has less energy spikes than the U-tensor. However, the most efficient is still CMSIS. To conclude our paper, we investigate the question of the feasibility of running deep neural networks on IoT devices for inference purposes. We found out promising results for small networks between 16 to 32 kernels. However, this can become quite energy intensive. There is a trade-off between framework automation and efficiency. And finally, the quantization method that we use is quite open for research. Thank you for your attention.